So let me grab this, put this out of the way. Right. So this is going to be dealing with Chapter 9. And Chapter 9 begins talking about the concept of remote sensing. And it's actually, the title is Remotely Sensed Images from Space, so, or from above. And so it's going to actually focus in on photogrammetry, because the other chapters will get a little bit more into other types of remote sensing. So this is just primarily photographic type remote sensing, as opposed to the other things, LiDAR and those kind of things. And so this is just kind of an introduction to that, and we'll talk about how it was developed through aircraft photography, or how that actually developed, because there were some other types of things that came in prior to that. And then we had different types of aerial photos, and for a while they've been used extensively from World War I on, and they kind of fell out of favor for a while with other methodologies coming in, but I think they kind of come back a little bit, particularly with UAV use, that a lot of people are using photographic type stuff for that. And then one of the things we'll look at is photo interpretation. How do you interpret objects from aerial imaging? And that's a really big topic. I mean, in the war time frame, those were big things that were developed through that. And then we look at the last thing, we'll look at measurements made on aerial photos. So things like distances that we can determine, and also heights. Those are kind of cool. And that's probably pure and applied what you would get to the term photogrammetry. So let's talk a little bit about remote sensing kind of images. When taking a picture, like with a camera, whether you're storing that image digitally or on the old photographic film, basically that image is captured and stored. And this is actually what you would call a form of remote sensing, where remote sensing basically just means you're acquiring data without direct contact. So there's a lot of different things that could fall under the classification of remote sensing. I personally think that even like if you're out there using let's say a reflectorless total station, you're doing remote sensing, but most people refer to remote sensing meaning that you're doing it from above. But basically it's just acquiring data without direct contacts. In other words, you're not out there with a guy walking around with a rod kind of deal. That's what it's kind of primarily saying. And so if you're using a camera in that traditional sense, the camera is sensing that picture on objects that are obviously some distance away. And so that object that you're focusing on is typically what you're calling your target. And as we'll see, there's a couple different types of remote sensing, but one would be what you would call active remote sensing, and the other one is passive. So what we're kind of talking about here is passive remote sensing. So what that means is there's the device that's actually doing the sensing is not producing any energy that is being bounced back to it. So what you're getting is strictly ambient light when you're using photography. Any of that light that's coming into the film or the CCD device that's capturing that is an example of passive remote sensing. Where active remote sensing is you got a device that's actually sending radiant energy out and it's coming back, such as LiDAR or an EDM. Those would be examples of active remote type sensing. So remote sensing is just that the process of collecting data, either related to reflected or emitted. Okay, so reflected would be passive, and emitted would be active remote sensing. What you're dealing with is the electromagnetic energy. We'll talk a lot more about that spectrum next week, but we'll get a little bit into that today. But whatever is happening, either the target that you're trying to get the information from, or the image is just reflecting information back, or you're striking it with data and it's coming back. Okay. So film photography is certainly an example of remote sensing, and like I said, it's passive remote sensing. It was developed pretty early in the 1850s, I believe, is when they actually started to develop film photography. And it actually, even up until the digital age, was considered pretty pretty much one of the best. Now then we push the limits on digital photography, so that's really displaced, but even high-level photographers were still using film photography as much as maybe 10 years ago. So digital photography has displaced that, a little bit different process because you have what's called a CCD, a charge coupled device. Basically, it's just an array of pixels that each pixel gathers a certain piece of the image. And the more pixels you have, the higher res picture, so that's where you get your what we call megapixels and those kind of things. Laser scanner, now that would be an example, of course, of something that is active. So laser scanner actually sends down laser light, it strikes an object and it bounces back up to it. And LiDAR is a type of laser scanner. Usually when we say laser scanner, that usually means terrestrial. A lot of times people are talking about terrestrial laser scanners, where LiDAR is almost exclusively used airborne. And also the LiDAR is becoming miniaturized to the point now that it's fitting on these smaller drones. So we're starting to see LiDAR used more than, not more, but we're seeing that used now in conjunction with photography as well. The human eye is certainly a remote sensing device, but it's a passive type, so all you're getting is whatever reflectant radiant energy that's coming into you. That's a type of remote sensing device. So aerial photography, that's what we're going to focus in on primarily. That's what he focuses in on this chapter. Aerial photography is just the process of taking photographs of objects on the ground from some airborne platform. And so this goes back to the early days of when photography actually started to be developed. Like I said, it was developed pretty well by the time the Civil War broke out. As you've probably mostly seen pictures, a lot of you have seen pictures from that time frame. So they really had developed it to a pretty high level. Although at that point they had to use those big glass plates with a lot of chemicals to do it. The film kind of idea came in a little bit later. But it's been used for over 150 years, at least. And this was first accomplished by getting something up in the air using balloons or kites. And they did do this in the Civil War, but they've done it even prior to that. So you'll see a lot of those older pictures. It's kind of interesting. Later, aircraft and rockets were used as a method of getting your camera airborne. And then we have high flying elevation satellites nowadays. So images can be obtained both by public and private sector. You have a lot of public sector government types of things that were deployed, especially during the wars. And a lot of that now has been declassified. So that information can actually be disseminated and used by civil users now, although a lot of it has to be paid for. I'm going to show you a website that you can use. Then there's, of course, certainly private sector people that are involved in that. And back when I was back in the late 70s, early 80s, and 90s, we were using photogrammetrists a lot. Companies that would fly your sites for you way before drones were in there. And those would be example of private sector. So aerial photographs certainly have been used for many, many, many applications. One of the big things that drove a lot of this was military. So it was used pretty early on for military reconnaissance. They kind of started doing that in the Civil War. They used to use big hot air balloon or balloons, helium type balloons, and they would send the photographers up high and do that. But it really came into its own in World War I. And that was when actually planes had been developed to the point where they were used quite a bit and extensively in World War I and World War II. That's what drove a lot of that, and then the Cold War as well. So we also used it for surveillance, and that was probably more so in the Cold War era, and I'm sure it's still used quite a bit today. And then landscape studies, scientific or for other purposes, that's a big thing that it's used for. Planning purposes, obviously. Civil engineers, like I said, we used it extensively. I'm sure a lot of you guys still use that. And updating geospatial data. So GIS people will periodically, like counties or whatnot, have their counties flown periodically, like maybe every 2-3 years, and do those photo updates. Quickest way to get your information and very effectively. and creating and updating maps. The USGS, by the way, if you've seen the old USGS maps, if you're anybody that has experience with those, they use those, the 7.5 minute quads. A lot of those were created in the 30s, 40s, and 50s, and you'll see, if it's still published in the 70s or 80s or 90s, you see big areas that have purple, the realignments of roads and stuff. Those were photo updates, and they usually have a photo update when that was done, and it may be done several different times during the life of that map. All right, so some of the first era of photographs that we had was done by a French photographer. He was taking pictures in 1858 in outskirts of Paris. He used a tethered balloon and took his camera and sent it aloft. Now remember, in those days, in 1858, they were using the big glass plates that you had to basically smear your chemicals on it and take it long exposures and those kind of things. And those photographs, unfortunately, no longer exist. But that was the beginning of a new form of data collection. So it kind of proved that that the idea worked. And then you had balloon photography. There were some things about it. Also, 1860 era took photographs of Boston. Photographer took some pretty good pictures. It's pretty interesting. I'll show you here in a minute. I think his name was James Black. But there were problems due to kind of related issues, exposure time. Those days, you had to do pretty long exposures to get a decent photograph. And of course, if you are doing a long exposure time and you've got movement going on, that translates to blurred images. So there were issues with that. And you had to have a proper landing location, but you would have gas interfering with your plates, the photographic plates, and probably temperature might have played into that too a little bit, because those chemicals, I'm sure, are, besides light sensitive, they're probably also temperature sensitive. They also experimented with kite photography using a series of kites that's developed in the late 1800s. The photographer was, of course, safely on the ground. A guy by the name of George Lawrence did a series of photographs in 1906 San Francisco. I think right after the big earthquake that struck, and then the fires ripped through San Francisco and basically leveled the city. There's a couple of pictures that exist of that. So this is a picture of Boston. This was done in 1860 by James W. Black, and it's pretty interesting. You can see Boston Harbor, and you can actually see the old clipper ships out there in the bay there. And then this was a picture of San Francisco, I think, after the earthquake. So the earthquake pretty much leveled downtown. And then after the earthquakes happened, if you've ever read anything about that, it just, fires just ripped through the whole town. And you had a lot of gas that set fires and all kinds of things. So it really, really did level it. So then we got into developing in aircraft photography. So after the Wright brothers developed the first flying planes in 1903, basically right up the road here, because they were housed in Dayton, and then of course their major first flight was considered down in Kitty Hawk, North Carolina. But they then went on and partnered with a lot of other people, but they really developed these aircraft quite a bit. And the first major area photography by passenger was done in 1908, and extensively used in World War I. And after the Wrights developed their planes, they actually really petitioned the federal government quite a bit, and it took the Army and those guys a while to actually come on with planes. But planes were used extensively in World War I by both sides of the conflict. But they were used a lot. Proved their mettle for map making, because you were able to effectively get large areas very quickly, very accurately, and then of course you could trace those and produce maps pretty much on the fly, more or less. They were used in military tactic planning, and if if you know anything about World War I, and extensively was trench warfare, so it was really brutal. And you had these trenches on either side, and they were pretty stagnant. Just it wasn't a lot of ground movement like you had more in World War II, but you still had tactical kind of issues that were going on. And of course, the trench patterns were important for artillery location. They were able to determine where they might need to do or want to do bombing, and definitely contributed to any kind of military intelligence. So this is an example of some of those released photos now that you can get that are available. And this is showing you from World War I era. I'm not sure exactly when the date of this would. I don't know if it says up there or not. I'm not really sure. It looks like 1917 probably. So I think you can see the trenches, and then these would all be just tracks of probably different convoys in and out of areas, reconnaissance, those kind of things. Extreme use also happened in World War II. Now, of course, the planes were much better. I mean, the planes were still pretty crude in World War I, although they developed pretty quickly. But in by World War II, the planes had become a really phenomenal tool. And so they were used by both the Allies and the Axis forces. And these were definitely used a lot for military action. And like I said, as World War II was a lot more mobile than World War I, which was really, like I said, it was pretty stagnant in areas. It would just trench warfare that went on for a year or more. You had a lot more going on and a lot more movement with World War II. And so this was a key reconnaissance technique that was used. And then they planned things like the raids on the V2 rocket base. So the V2s were the rockets that the Germans had developed, and they could reach England real easily and those kind of things. So they had planned raids in those areas, and also other types of munitions within the German occupied area. Dam locations, major parts in the cities, anything that they could target, they could find this through that reconnaissance. Now, there's a good source, as we said, of historical imagery that's available now through this. It has been released in this group called the Aerial Reconnaissance Archives. I think if you click on this is in your book, but it's through the government of the UK. And I could launch it. I did actually before I got in there. You can get on there. You can't really see much. All of this stuff you can kind of visualize or view them, but they do require you to log in now. And actually, any image that you want to use, it costs. So it's not like it's free or anything. But they have literally, I don't know, there's probably hundreds of thousands of images that have been declassified and that can be used. And I think this is primarily World War I, but they may have World War II stuff in there as well. So that's might be, if you're interested in some of that, you might want to check that one out. Okay, so post-World War II use, obviously after the war, then we went into the kind of the Cold War era, and that was a big deal for the United States in particular and other countries. But this was used a lot. Aerial photography was used a lot for Cold War spy mission by both sides, primarily Russia and the U.S., but it was also other countries I'm sure were involved. So in the 1950s, they developed what was called the U-2 spy plane. The U.S. did, and some of you guys have probably heard about that one, but that one was a big deal, particularly when it got shot down and the pilot was Gary Powers was ejected and landed in Russia and was taken prisoner, and it was a big deal between Russia and the U.S. But the U-2 spy planes were capable of flying at 70,000 feet above the ground, and but this one actually got shot down. This was used over the Soviet Union extensively. And of course, they used them during the Cuban Missile Crisis. That was where they determined that the Russians were developing those the missile sites over in Cuba, and also were looking at placements of missile launchers. And that was a pretty tenuous time. I think it was like in '63, something like that, when that happened. And I mean, we were pretty much on the brink of a nuclear war at that point. A lot of people don't even realize that actually happened, but that was pretty close. But they used spy plane technology for that. And of course, it continued to develop. They developed the Lockheed SR-71 Blackbird. This was capable of flying 80,000 feet above the ground, traveling twice the speed of sound, and it had a pretty weird configured shape that was supposed to be undetectable a lot of times through radar kind of stuff. A lot of these have been retired or decommissioned, yeah, because they've changed the technologies. Also, they used a lot of different materials. I think a lot of those use composite, carbon fiber composite stuff that also is hard to detect on radar. So they've experimented a lot with that kind of stuff. This is a picture from the Cuban Missile Crisis era. This was 1962, and this is down in Cuba where they had determined that that they were setting up. They were actually setting up missiles that were just, and it's not very far from there to, like, say, Miami. They're on the range. But you can see they had launch pads here, and they actually had missiles. Everything was in place. And in fact, the Russians actually had ships with missiles on their way over to deploy them. That was when Kennedy and Khrushchev got into that. So this is a picture of the Blackbird, the SR-71 Blackbird. And you can see the shape and all of that. So it was doing a lot of reconnaissance until it was retired. Okay, so current use. So now a lot of this is done through digital aerial photography as opposed to film aerial photography. So again, there's a little bit of a difference. Obviously, digital is no development time. That's one of the big deals. And then, of course, it can be very, very good stuff because you can have like your megapixels. So the higher that is, the better it is. But now we can obtain it through unmanned aerial vehicles or UAVs. And of course, a lot of civil users are using that. Some of you guys are probably using them now. So in this case, the planes are piloted from the ground via remote control. Now, of course, the military doesn't have to worry about beyond visual line of sight like we do as surveyors and civil users of it. But all of this has developed out of that. It was used extensively in Iraq and Afghanistan, and there were numerous types of UAVs developed and deployed. The Predator, the Global Hawk. So some of them were used for bombing purposes, and others, or missile, and others were used for surveillance. Now, data collection for civil use includes federal, state, local governments, as well as, of course, just civil users. And of course, we're using the typical drone technology. Okay, so this is a picture of the Global Hawk. That's a pretty good sized drone, but it's unmanned. And of course, this would be a civil user. That kind of looks like one of those. I forget the one, but that's a fixed wing aircraft, which a lot of surveyors aren't using. We're probably using more the rotor type. Okay, so what are some of the different types of aerial photos? So we want to take a look at that a little bit. So basically, if you are looking straight down under a plane with a camera, that's going to create what's called a vertical photo. Now, you do get relief displacement with this stuff. We'll talk about that a little bit. We're not going to get into that too much, but you do have some what we call relief displacement. But a vertical photo is primarily a photo in which the camera is looking straight down at a landscape. And essentially, the direction that the camera is looking is following the direction of gravity. Okay, so you would call that vertical. And of course, with like drone technology, you now have, it's very sophisticated, so it can sense when it's off a little bit. So it keeps the camera pretty much in a straight down view. The location directly under your camera is referred to as nadir, which is the direction that gravity is pointing towards, essentially. And that's the direction of the vertical line. Then several other types of aerial photos exist. Now, this really probably talks about more the film type or the electromagnetic radiation that it's sensing, okay? So not so much like a vertical photo or what, but this is what it's talking about. So when we hear the term panchromatic, what we're looking at is this is thing that captures all of the visible portion of light. So pan basically means everything. So panchromatic that means everything. Chromatic is usually meaning multiple colors, those kind of things. So basically, what you're getting is a grayscale image with a panchromatic type of film. So if you were using the old film photography, you had to get a type of film which was called a panchromatic type film. And color came about a little bit later because the earliest stuff was black and white, and then later they went into panchromatic. But color, of course, is capturing basically three main bands of visible light energy. And essentially you're just getting reds, greens, and blues. So that's essentially what we usually perceive as humans. And so the colors are composited together as what we call true color composites, and that's what you're seeing essentially. Then you have what's called color infrared photos, or CIR. This is a specialized type of aerial photography, and again, in the film type thing, it was based on the type of film that you use. You had to have special color infrared film. And I think with like digital, it's essentially done, I believe, with filters. So it's pretty easy to do if you're using a digital type kind of concept. So this captures both visible light, but also infrared light. So infrared light is above what a human can see. So we can't actually see infrared light, but you do have to use a special film if you're using traditional film. And so it is invisible to the naked eye, but the cool thing about it is that it just brings out all kinds of detail and things that you can't see that are actually there. One of the really interesting things is that like a lot of insects can actually see infrared. So like honeybees, they have an infrared component in their eye that they can actually see infrared light. And there's all these, they've taken pictures of certain types of flowers that when you take them with infrared, you have these, like they call them nectar guides. They're just like arrows that point directly to where the nectar is that you can't see on the typical petal of a flower, but an insect can see that, and it just guides it right into where it needs to go. So that's because they can see in that infrared portion of the spectrum, and we can't. So you can use a special filter to see reflected infrared energy on a CIR photo. And near infrared is, in this case, is going to be reflected and displayed as red with this type of filter. Red reflection is going to be displayed as green. Green reflection is going to be displayed as blue, and blue is going to be blocked and displayed as black. So you get these false color composite kind of things. And so what you're seeing is the observed color is going to be black, but the actual wavelength is blue. So like a water would be giving you a blue signal back, but what it's going to do is going to filter out to black on the infrared. And anything green becomes blue, anything red becomes green, and near infrared becomes red. And you generate these actually very interesting pictures. So this is extremely useful for things like environmental studies, particularly when you look at the vitality of vegetation. Infrared reflection is used to generate the health associated with vegetation. As we'll talk about next week, certain plants, if they're healthy, they'll produce more red than less red, those kind of things. And by using these with color infrared, you can determine, like flying over a forested area, and you can see where healthy trees are versus not healthy, or the whole ecosystem, whether it's healthy or not, based on that. So bright red sections indicate high, what's called NIF reflection, excuse me. So things like grasses, trees, or healthy agricultural fields, they're gonna produce a bright red. And if it's not, then you're gonna get less of a red color or even not a red color. Black sections are going to indicate that all light's absorbed except for blue. So again, things like water courses, they'll do that. And likely lakes, ponds, streams, or rivers. White or cyan usually indicate varying color reflection. So that could be different things, but it might be like developed areas, rooftops, roadways, those kind of things. And barren fields. So this is an example of a picture using that technology where it's taken with a infrared. This is a color infrared aerial image of, happens to be in an area of Idaho. So you can notice that, first of all, the water course that's coming through, which would typically, we would probably perceive that as a bluish color, is black because it's absorbed all of that and reflects it back. So where healthy vegetation exists, you notice it's pretty red, and you can notice that, you know, that's a big pivot irrigator there. So that's probably some kind of crop growing on here, and a lot of these are crops. You notice also a lot of areas where there's an area where it's a barren field, that's probably a pivot irrigator as well. But then you get over here and where the city, you can see a lot of gray, a lot more grays, those kind of things with the roadways. You can also see, because this is a U.S. Public Land Survey state, you can see a lot of squares and rectangles in here. So there's actually big sections. You can almost see the sections, right? That's probably a section right there. That's probably a 1 mile by 1 mile right there, broken down into quarter sections and those kind of things. So this stuff really shows that up very well. So due to distortions within your photo, you can't necessarily use it for mapping directly. So what has to happen is we have to relieve those distortions or somehow rectify those out. So that can be a big process too, but we're not going to get that involved. But what you need to understand is that photos are not going to have the same scale at all points. And a lot of that is due to the fact of the relief of the site. And also the scale is going to change drastically as you go across the photo, okay? So because some features are closer, others are farther away from the camera, that's your you get your relief issues. And also because the center point of the photo is only going to be the exact scale, but anything coming out from that is going to change drastically. So, and that point of the center of the photo is referred to as the principal point. And that's the point of where your nadir is essentially. And what you'll also get because of that is what we call relief displacement. So tall objects located away from the principal point appear to be like leaning toward the edges, or it almost looks like the buildings are falling away from the principal point. And that, again, that's just that's an aspect of that relief displacement and the fact that, you know, your scale factor is changing drastically from the center of the photo out. So we get that concept of relief displacement. Here's a good example of this. You can notice your principal points essentially right here. And what's happening as we go further away, so the scale right at that point of the photo is a 1-to-1 essentially. But anything as you're measuring along this line this way, it's actually kind of a changing scale. But you can drastically notice how these buildings look like they're falling away from the principal point. And that's that concept of relief displacement. So to be useful, they have to get rid of that relief displacement. So they'll produce what are called orthophotos, where they take and rectify that out. And we're not going to get into you know, how that works. That's probably done mostly by computer algorithms nowadays. But okay, so relief displacement, effects seen in the aerial image where they appear to bend or move away. And photos that have removed that condition are called orthophotos. So what most mappers are going to use, what the raw photogrammetrist is going to give you or is taking when they're out there taking images is just a normal photograph that's going to have relief displacement. So if you're going to use it for any real purpose, you're going to generate an orthophoto. Even if you guys, any of you guys that are using drone orthophotography or photography, you're probably running it through a program such as Pix4D or something like that, where you download the images into there. It stitches the images together, but it also converts those into orthophotos, and that's a big process. Anybody using any of that software right now?
No.
If you have done it,
I'd be interested in it. But
well, if you have done it, Ben, what it takes, I mean, hours to do, because you have to, depending on the number of series of photographs you have, but you download them into the software essentially and let this run maybe a day. And what it'll do is it'll stitch your photos together because there's overlap in those photos, and then it also uses those to remove that and produce what's called an orthophoto mosaic. So it's pretty cool, but I mean, it's all done by algorithms. You don't see a lot of it happening. You just see the end result. So this process where you're taking that, producing those ortho photos is called orthophoto rectification. And so what this does is it takes that scale that's uncommon or constantly changing, and it produces a uniform scale across your photo. And once you have a constant scale, then you can start using it for mapping purposes. And so you can get that to that point. So a true orthophoto removes all the effects of relief displacement. And it gives you the appearance of looking straight down, but everything's going to be not bending. But so what it does is it uses several images to fill in missing information. Also, when they take a series of photos, I'm sure you guys are aware, but when you take a series of photos, there's an overlap. So as your plane is flying, it's taking its time so that it knows the velocity of what it's flying at, and the shutter is going off enough so that you usually get like a 60% overlap front to back and a 60% left to right, something like. There's different formulas that people use. So orthophotos are used to create special products called digital orthophoto quads, and you can buy these from companies that do this exclusively. So these cover 3.5 or 3 3.75 a minute latitude by 3 3/4 longitude. So that's the size in area of that. So that's a minute of arc is what that is. And this would be something, a product like the USGS would offer you. So that's 1/4 of a 7.5 minute USGS quad. So these DOQs, they're geo-referenced so that you can link those up with other geodata sets. So if you are doing mapping of some kind, or you're a municipality or something, you can buy digital orthophoto quads, and you can download those into a lot of GISs will read them, or you can get a special reader. Like there's a program out there called Mr. SID that a lot of people use. They can download digital orthophoto quads into that. Stuff can be digitized and then whatever, so that it can be used for mapping purposes. So the USGS produces products that cover the entire quad. And then I don't know if they're free. Those might cost. I'm not sure. All right, so when a camera is not positioned in nadir, but it's angled, then you get what's called an oblique photo. And so in other words, we're not looking straight down, we're looking in at some angle. And this image is what you call a perspective view. And this allows you to get sides of buildings. In fact, a lot of people that are using drone photography, if you're flying a site and you cannot get everything in a nadir position, they'll go back and fly, like say around a building, and they'll take oblique images, and then they'll stitch those in. They stick those into Pix4D, and it'll rectify based on those, so it fills that in with that information. So it's pretty incredible how this works. But those oblique image photos are actually very useful, and we can use them for a lot of purposes, like law enforcement, gathering information. Private companies, we use that for collecting different type of data. But like I said, I know a lot of drone people will use that because it really does help infill information that you can't just get in straight nadir position. So here's an example of the Lincoln Memorial, I believe, that's taken in as what you might call an oblique type photo. And you can see what this allows you to do. See the stuff like underneath the porticos and everything you couldn't see normally if you were in a nadir position. But by taking this, you can infill this with your digital ortho photos, and then it allows the software to blend that stuff together. And in that picture, San Francisco was a grand example of an oblique. All right, so I'm going to talk a little bit about photo interpretation. And that's kind of what we're going to be getting into for the lab. We're going to do a little bit of this, and it's just going to be talking about primarily what you see on a photo and how you interpret it and those kind of things. A lot of this was developed out of wartime use. And So that was a big area. That was a big deal. Photo interpreting people. I mean, they made a lot of decisions based on what they saw. For instance, like the 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 thing we were talking about with the Cuban missile crisis. I mean, if they had not discovered that, that could have been a major thing. So photo interpretation is big deal, but it does take a big skill set to do this. Like I said, those kind of people were really worth a lot at the time, and the government spent a lot of time developing that and developing the people to be able to do that. So when you look at objects viewed from above, they certainly take on a completely different appearance than when you're viewing them head on or from the ground level, like as we're all used to seeing. And I'm sure you've seen this, but I know it's always amazing to me when I'll go look at something, I like looking at Google image pictures or something like that of an area that I know really well, from the ground, and then you look at it from the sky, it's like, wow, that really like has that bend, and like you look at a river and those kind of things, that's pretty amazing to see all that. But complex patterns can look completely different from the ground and then from above, and sometimes the complexity you don't even see. So if we're looking at this picture, for instance, a lot of you might be able to tell me what this is, but this happens to be looks like a very tall object, as you can see. And then it has that shadow, so that's kind of indicating what's going on there. And you got a pretty large complex of buildings. Probably looks like there's a couple of swimming pools here. And of course, you're in a pretty urbanized area. But when you look at that from that point of view, what you're looking at is a Space Needle in Seattle. So looking at it from this point of view, if that's all you have, let's say you're doing, reconnaissance for spy missions, this doesn't necessarily look like that. So developing the techniques kind of things is interesting. And if you look, this is kind of interesting. When you look at this, you can see there's the swimming pool here, and back in the other view, you could see that as well. So when we look at this, interpreting your features on remotely sensed data, you have to develop that visual image interpretation kind of sense. And that visual image interpretation is just the process of discerning information from objects that you're looking at based on what we would call distinct elements or distinct types of sets of things that you are observing. So we have things like pattern, shape, sight and association, texture, size, tone, and shadow. We're going to kind of take a look at each one of those as we kind of step through this. Okay, so the first thing we would see is pattern. So pattern is going to be a physical arrangement of the way certain objects are, maybe in an image or on an image as you're looking at it. So the pattern of objects and how they're arrayed is going to definitely tell you a lot about what you're looking at. For instance, a series of cars that you see parked uniformly in a lot, it could indicate a lot of things. I mean, one could be a car dealership, or it could be a sporting event area where you've got cars parked in that parking lot or some kind of thing like that. Evenly spaced planes in an airstrip might be an example of a military base. Haphazard arrangements may point to other things as you get into it. Sight and association. Sight represents your location characteristics, and you're going to see other objects that might be nearby in the image. So where my sight is and the things that are associated with it. So things like a distinct object such as a football field. I mean, that's pretty obvious kind of thing, but you see bleacher arrangements, number of seats, and the parking, that may indicate what that field is used for. So it could be like, say, maybe high school. It could be potentially college. It could be NFL. So the size, the proximity, all that kind of stuff could come into play there. And then we have size. Physical dimensions of length and width allow you to decide whether you're looking at something really big or really small. And especially if you can get something that is pretty visible and you know exactly what you're looking at. So the relative size is going to yield clues to other aspects of the visual interpretation. So there you go. An average car might be 15 feet long. So if you kind of know that you can find a car pretty obviously, Then you can compare that to other features and get an idea of scale, size, and those kind of things. You can identify, let's say, a football field, that's 100 yards. Well, when you start comparing that to other objects, and again, you've got a scale reference right there. So it gives you that reference that you can use. Shadow. Now, shadow casting, that fact of the light shining onto an object and then casting a shadow can give you ideas about things, provide information about height or depth of objects. It can also, you can determine things like time of day and also time of year based on shadows. Now, shadows can be really a big deal, especially with photogrammetry. Back in, like I said, in the day when we were using a certain photogrammetrist for a project that we were working on, this was probably back in the late 80s, I'd say maybe mid 80s. We were trying to get a site flown to get a topo map because we were doing a big subdivision. So we needed to get a photogrammetrist in there. And this site happened to be right in the flight path of the airport, the Greater Cincinnati Airport. And the other thing is, it was probably about maybe February when we were doing this. So we had a real small window of time when you could take the picture, because the two reasons. One, every time the plane would try to go take pictures, they'd get bumped out of the airspace because the jets had precedent. And the other thing is, if they didn't do it at the right time of day, you'd get shadows that just killed it. So this site was really, really treed. And I think the first couple of times they actually were able to get out there and get photos, the shadows were so intense that they weren't able to do anything with the data. There was no way they could determine anything. So, and then they kept getting bumped in their airspace. So it took them about 4 flights before they actually were able to get that. So shadows can be a big thing, a big problem actually. And the other thing was photogrammetry. If you're doing ground photogrammetry where you want to get topographic data, you really have a limited time to do it. Sometime in maybe November, December to maybe March around here, if you want to see the ground. And in fact, with things like some of these aliens, like the honeysuckle, that stays green a lot longer in both later and earlier. So that can be a problem. But tall objects photographed from above are going to be partially hidden. Shadows will cast to tell things like tall features, like we saw with that tower. And it can help to identify structures such as railings or utility poles. But like I said, it can also have a detrimental effect. And this is the thing we dealt with quite a bit with photogrammetry. So shape is another thing that you can use for aerial interpretation. The form and the shape of an object or objects. Distinctive shapes can greatly aid in the interpretation. Things like a diamond shape of a baseball field, that's going to quickly identify it, or a racetrack has that circular kind of thing. Circular crop fields indicate a pivot irrigation system, like we saw in that color infrared image we looked at. Oval shapes might be some kind of racetrack. Could be horse track. It could be, a track and field kind of thing. So texture refers to your differences in tone throughout your image. And it's probably easier to see texture when you're looking at color images, but it also shows up in black and white or grayscale. But it can be identified as coarse or smooth, particularly different types of greens with vegetation may be distinguished. Forest of trees could look rough. A field of grass have a smooth look. Water features may distinguish a smooth lake or a rough rocky shoreline, or even something like a river. If you've ever looked at rivers, particularly where rapids or waterfall areas are, that's going to show up pretty directly on your photo. So tone, grayscale levels or ranges of colors. Light blue, swimming pool. Wooden walkway is going to have kind of a brownish sandy tone. Okay, so we're looking at this. This is just kind of a little example, and we're going to be kind of doing this on this lab that we're going to be doing. You're going to be given several different images, and we're going to look at them and kind of determine them, looking at through those different types of processes. So you guys might be able to tell me what this is already, but this is an interesting picture because we're seeing a lot of those things. We're seeing size, we're seeing shape, we're seeing tone, we're seeing shadows, we're seeing site association, as it looks like there's some kind of city here and not a city here. So as we go through this, we'll kind of think about that and see if we can resolve that down to what this is. Like I said, you guys probably already know what this is, but if we look at this, just consider this image. And if we look at that, so if you apply those interpretation things to that, let's see what's being shown. There's a pattern there, and we see that there's three main objects that are arranged in a definite pattern. So we go back and look at that. Here's your three main objects, one here, and one here. And they are in some kind of a pattern, not necessarily a really highly defined pattern. Texture around the objects, it's very fine as opposed to the north and the east. With tone there, a rare area around those objects, again, it's much lighter than north and east. Probably indicates sand. Site and association, those three main objects, they're located in that largely sandy area adjacent to looks like what's probably a city. Size, the size of those objects as compared to buildings indicate they're really, really large. And their shadows, okay, so the shadows cast indicate that they're pretty tall and distinctively shaped. And the shape themselves, the objects have a square base, but it looks like they're a pyramid shaped. And so when all of those elements come together, what you're really getting is this, the Great Pyramid of Giza in Cairo. And again, so we're gonna be looking at those kind of things. I want you kind of think about that, and we're gonna step through those as we get into our lab exercise that we're gonna be doing. But it's kind of interesting because you're gonna look at some of those photos and you'll say almost know what it is without going through those concepts. But then other ones, if you have to rectify that stuff, it's going to take you a while. And some of them you won't get every one of them. But we'll look at that on Thursday. So that's what we're looking at. There's your this is the city, Cairo. It probably is a park. You notice that's your sandy areas, your shadows, all of that. And that all comes out. So the last thing we want to take a look at is using measurements or making measurements from aerial photos, because we can do that to do several things. One is to determine a scale of that photo, which can then be used to measure basically horizontal distances. And then the other thing is it can be used to determine heights of things. And that's pretty cool because you can do that based on shadows. So this process is what we call photogrammetry. That's what that term means. Basically, photogrammetry, photo measurement. That's literally what that's saying. And it's used to determine things like the height or depth of objects, but also distances across that photograph. Now, the first thing you have to do is know what's called the photo scale. And that's the that's the representative fraction essentially used to determine how many units of measurement on the real world correlate to the equivalent unit measurement on the aerial photo. So basically it's just coming up with that representative fraction or natural scale that we talked about with mapping a couple of classes ago. So for a scale of 1 to 8,000, what we're saying is 1 unit on the photograph is 8,000 units on the ground. Okay. If you're using an inch scale, you're saying 1 inch on the photo is 8,000 on the ground. Scale is going to be dependent on several things. One is the focal length of the lens. Okay, so that will really make a difference and determine that. The other thing is the altitude that the camera was above the ground when the photo was taken. So those two things are very critical. And in general, the higher you go, the more detail or the more area you see, the less detail you're going to see. For an unknown scale of an orthophoto, that can be determined using a secondary source as long as on that secondary source, such as a map, you're looking in the same area where you have your orthophoto. And again, key term there is you have to have an orthophoto to do this process, because if you have an unrectified photograph, remember the scale factor across the photo is not going to be true. So if you had a USGS topographic map, though, we could use this as a secondary source to determine a representative fraction. Now, the other thing you could do is if you had, like, say, 2 intersections that were visible in the photograph, and you knew that distance because maybe you had shot them with, like, say, your EDM or something, you could use that as a way of representing this as well. So to determine that unknown scale factor, it's just using a real simple technique. Your representative fraction is equal to your photo distance divided by your ground distance. Okay, so your photo distance is that distance that's scaled on the photo, and remember that has to be an orthorectified photo for this to work. Your ground distance would either be a real world distance that you've measured, like I said, out in the field, you've measured two distances that you can see prominently on that photograph, or you scaled them on a, like I say, a USGS map that you can also find the same two intersections on that. And then the RF is your representative fraction, or we also refer to that as a natural scale. So for example, let's say you've selected a feature that's visible both on your map and your ortho photo. And on your map, you have a map scale that is a 1 to 12,000. So that's your map scale. And you've measured 59 inches on the map between, let's say, two intersecting streets. So that's going to be equal to 7,800 inches on the ground. So if you measure the same distance on the ortho photo and it measures 1.77 inches, then basically the 1.77 divided by the 7,080 yields a scale factor essentially of 1 to 4,000. Now, I'm sure it wouldn't always come out to be a perfect number like that. So, but this is just a little example, okay? So once you know the scale factor of the photo, then you can use that to measure anything on that photo from that point on and determine distances from it, okay? So that's the process of simply taking an unregistered ortho photo and getting it to a natural scale that is then usable across that photo. Okay. So photos can also be used to pretty accurately calculate height of objects. And the cool thing about this, you're going to use shadows, and shadows are going to be used for this purpose, but you don't have to know the latitude, which does affect your shadow. You don't have to know the time of day, which also affects your shadow, and you don't have to know the date. All of those things can be used to determine this stuff, but actually we don't need it if we're just looking to try to get height measurements. All we need is three variables that are critical for this. You just need the photo scale, which we just saw an easy way of determining photographic scale. We need to be able to clearly see a shadow that you can measure using that photo scale. And then you just have to have the knowledge of the actual height of an object in a photo. So that might actually be the harder process. So for instance, if I was downtown in an area where I knew I had a tall building, and I got this ortho photo that it's casting a shadow on this, I would have to know what the height of that building is to do this process. Okay, so I could go out and measure that if I needed it, but that would be the hardest part, because getting the photo scale is pretty simple, and being able to find a pretty clear shadow and measure it's not that big of a deal, but knowing the actual height can be a problem. Okay, but what you're doing is, by determination of this, you can just use this simple process. You can just essentially say that the tangent of your alpha angle, which is the direction that the sunlight is coming in on your object, is equal to your height divided by the length of the shadow. Okay, so that's your angle of the sun, the height of the real world object, and L is the length of the shadow. So angle of the sun is going to be changed based on latitude, time of day, and what was the other thing? Anyway, the third time of year. But if you know H and you can measure L, you can determine alpha, and so this becomes independent of those other three variables. So basically, you're just taking example of that. Now you have to have the scale factor first off. So you have to know the scale factor of the image, okay? So this is showing you if this represents a high building and the sun's rays is clipped out like this, this ray is going to be that alpha angle right here with respect to the horizontal. So we measure the length of the shadow, we know this, we can determine that alpha angle. And then by determining that alpha angle, so you've got a map scale 1 to 4,000. L is measured on the photo. It equals a tenth of an inch, so that turns out to be 33.33 feet. And we know the H of the building, it's 115 feet. We can determine that alpha. So the tangent of alpha is 3.45, and then you can use that to determine heights of other buildings. Because that angle is going to be the same anywhere on the photo. The ray of the light coming in is going to be the same. So once you have this is a constant. So this is like a constant as the photo scale is a constant. That's a constant for your angle of your sun. So if you have another unknown building and you are able to measure the shadow of that building, you can just plug it back into that equation and you know the tangent of that. And you can just solve that to be a height of 46.6 feet. So that's a pretty useful little tool right there. So again, photo scale is important and height of building is important. Okay. And that gets you your total height. So there's your tangent, h divided by that. Okay, so any questions anybody has?
Nope.
Okay.
I don't think so.
Okay, well, read chapter 9. We're going to be, like I said, we're going to be going through this. We're going to be doing some images. If you want to go ahead and look that section over, there's going to be some images that are going to be given to you. And there's going to be 10 questions that you're going to answer based on that. So I'll be doing that Thursday. And then the other thing I'll be doing on Thursday is we'll go over the test first thing. Okay, so I haven't even had a chance to look at them yet, but I will get started on those tonight, and I definitely will finish those for Thursday. So, and so I'm going to go ahead and I'll get this recorded or get this recording done and load it out onto the website. And if anybody has any questions, I'll stick around for a bit. Otherwise, you guys are free to go, and I will see you guys on Thursday.
All right. See you Thursday.
All right,
Talk
great.
to you
Great.
Thursday.
Thanks.
Absolutely. See ya.
See ya.